The next topic we're going to look at is electron transfer in inorganic chemistry. Now, it's basically redox chemistry, right? But with a twist. Of course, it's more beautiful because we look at it in terms of beautiful mechanistic details. In terms of looking at electron transfer between species in inorganic chemistry. Okay, and basically there are two mechanisms. So today's all about mechanisms, right? Mechanisms of substitution, mechanisms of electron transfer. And we have two mechanisms in electron transfer, outer sphere and inner sphere. Okay, that's very simple. So it's not as complicated as what we just had with substitution, all these different things. In an outer sphere mechanism, essentially you can imagine you've got two species, or two complexes, coming close together, and the electron just hops over. It tunnels. It tunnels through the solvent, or it's a tunneling process. It's called an outer sphere process. In an inner sphere process, right, we actually form a molecular orbital, a bond, between the two species, and in order to do that, we need to have, on the one of the two reaction partners, a bridging ligand. So you've got to form some sort of a bridge between the two complexes where one of the ligands on one of the complexes actually forms a molecular orbital, bridging the two metal centers together, and after that has happened, you have the electron jumping over, and that we call an inner sphere electron transfer process. Now, the requirement for an inner sphere process is that you have two reaction partners. One must have a bridging ligand of some sort, could for example be a halide or a thiocyanate or something, some organic molecule. The other thing you require is that the reaction partner where that bridge is being formed must be labile, substitutionally labile, and we'll see why in a minute. But those are the two mechanisms of electron transfer in organometallic and inorganic chemistry generally. Now, here we see it in a little bit more detail. That's from Schreiber and Atkins. Let's start off with the outer sphere, because in a way it's mechanistically much easier. You can imagine two complexes coming together. They sort of associate with each other in space, but they don't form a bond with each other. In an outer sphere mechanism, no bonds are made or broken. It's just a tunneling process. Nevertheless, these two species that are associated with each other, kind of similar to what we saw in the Eigen-Wilkins mechanism with that complex that we formed. Remember, it's something similar. They come together, sort of encounter each other. It's some sort of an encounter complex. We call it a precursor complex. And then basically the electron bounces over, right? And after the electron transfer has taken place, basically what the consequence of that would be is that the electron, of course the oxidation states of the two metals will be different because you've shifted an electron from one metal to the other, and you end up with a successor complex. Now that's basically, these are just terms. The precursor complex is when they come together, then the electron transfer takes place, and after the electron transfer has taken place, you have a successor complex, and then they diffuse apart. And you've got the two products. So it's a beautiful mechanism, isn't it? They come together, they exchange electrons, they go away. It's kind of like a mating dance. With an inner sphere mechanism, things are a little bit more complicated. So you have a complex that has a ligand capable of forming a bridge. That's important. In this case, it's denoted by this red atom here, or this group here. And the other requirement for an inner sphere electron transfer reaction is that on the other reaction partner, that the reaction, or that the ligand sphere is, that the complex is relatively labile. And the reason why it has to be labile, substitutionally labile, is because watch what happens. The two come together much in the same way as we have in the outer sphere mechanism. They sort of come together forming this precursor complex, which is nothing more than them just diffusing together. Essentially, this is, again, analogous to the encounter complex we see in the Eigen-Wilkins mechanism, if you will. What happens here, however, which we don't see in the outer sphere mechanism, is that you then have this atom or this group here which is capable of forming a bridge, and that blue atom gets displaced, or that group. In order for that to happen, the complex has to be labile to substitution. Otherwise, that's not going to happen. Do you see that? You all see that. If this complex was substitutionally inert, remember that table I showed you earlier with that range of exchange rates? If this complex were inert, that would mean that this step could not take place easily. Because for this bridge formation to take place, I have to displace one of those ligands. And that's not going to happen if a complex is inert. It's going to happen when the complex is labile. Important. So we need a labile reaction partner bearing ligands that can be eliminated so we can form the bridge. So that's the next step. After the bridge is formed, then the electron transfer takes place via the bridge. So that's amazing, right? So you form this bridge, the electron bounces across, and then what happens is you end up with a water molecule, or the ligand that was eliminated here in this step from this reaction partner, going to basically sit on the original reaction partner. They basically swap partners, and then they diffuse apart. That's the inner sphere mechanism of electron transfer. Okay? Now, again, let's start off by discussing an outer sphere mechanism. This is basically what I've written here, expressed in a different way. I think this is a very nice way of contrasting the two. I really like that. The new Shriver and Atkins is really excellent. I have an old version from like 15 years ago, and I was looking at it last night, and if one compares it to the modern version, it's just dramatic how improved it is. So it's really a nice textbook. This is basically sort of the whole thing looked at in terms of reaction partners. So here we can, for example, see we form a precursor complex, the electron transfer takes place, resulting in a successor complex, and then they diffuse apart. So the outer sphere mechanism is actually quite straightforward. Before we move on, I now want to actually just, I think you guys probably find it very amusing that I'm going to use the overhead projector now, but the reason is that where I come from, and I think Mitch can confirm that, that's true. We don't use, they still use overhead projectors in Cologne, right? Exactly. So, sorry about that. I come from an old-fashioned place where we don't use PowerPoint. We still use, and I had to really hunt for one of these, right? So this is really, so when last did you guys see one of these, though?
Wow, what's this?
I haven't seen one since primary school.
I've never seen.
I have one at home.
Do you have one at home? Really? Why?
Because my dad is a teacher and he used it as a...
All right. So anyway, let's have a look at this. Because I mean these. Let's just look at it again from a different perspective. Oh, look at that. It's not very clear, right? Okay, let's try something else because I think these slides are very old. So, that's better. All right. All right. So this is basically looking at the thing from. Can everyone see that? I guess so. Yeah.
Yeah. You might want to dim the lights a little bit.
No, I can.
So this was just for Mitch because he's in Cologne. So okay, let's dim the lights a bit. That better? Right.
Yes.
It's a much more cozy atmosphere.
Bend the microphone or not?
Should I turn it off?
No, like, can you bend it in this direction? Or like do the whole, yeah.
Okay, now, this is the energy profile of an inner sphere electron transfer reaction. notice what's happening. I mean, can you see this?
Yes.
All right. Notice what's happening. The first step is the ligand association. The second step, and we go through an intermediate, we form this bridging complex. The next step is that the electron transfer takes place. Then the bridging complex breaks apart, scission, we call it, and then we form so it's a multi-step process, the inner sphere electron transfer mechanism. And what I want to actually just show you now is I want to look at actually some values. Well, before we do that, let's look at now the free energy profile of an outer sphere mechanism. It's much simpler because we don't have this bridge formation. We basically, you see, it's not very clear, but essentially you can see we form the precursor complex where they diffuse together, remember, from that first diagram I showed you. The electron transfer takes place. We form the successor complexes where they're still sort of associated together, but the electron transfer has just taken place. And then they diffuse away from each other, and you end up with the products. So, what's the take-home message? In a sphere, we form a bridge. We need one of the reaction partners needs a ligand that's capable of forming a bridge. The other reaction partner must be labile to substitution. An outer sphere mechanism, we generally don't have we don't have ligands that are capable of forming bridges, and yeah, you can very readily actually see the difference between the two mechanisms. Okay. Now, so that's sort of looking at the characteristics of inner and outer sphere reactions. And now I want us to look at some actual values. Okay. Now let's start off with some actual experimental examples of what we call self-exchange rate constants. This is not self-exchange, just rate constants associated with these redox processes. Have a look at them. All right. So this is the rate constant measured for the electron transfer. This slide is about 6 years old, right? So it's really, used this in Bonn, actually. Look at this. We go from a very, very small rates to very high rates, again through several orders of magnitude. Now, look at this example here. Now, chromium 2 plus COEN3, right? The question is, why are these reactions occurring with such a very low rate? And as we go down the table, these are occurring with such a high rate. That's what we have to try and understand and rationalize. Now, we exclusively right now discussing an outer sphere reaction mechanism. All right, we're not dealing with the inner sphere right now. So bear that in mind. But the question is, why is this happening? Why do we have this discrimination of the rate constants of these electron transfer reactions? Now, the reason is, it's got to do with reorganization. That's not very clear, I'm afraid, but it's got to do with reorganization. Structural reorganization. Here we have if we imagine, this is called a self-exchange rate, self-exchange electron process, where I'm exchanging an electron between two ion hexa-aqua complexes, 2 plus and 3 plus. All right? And the rate constants associated with that electrochemical process is 4. If I now take, for example, let's take this complex down here, chromium hexa-aqua 2 plus, chromium 3 plus. This process over here has a rate constant 10 to the minus 5, so several orders of magnitude lower. Then they exchange between an ion 2 and an ion 3. Ion 2, ion 3, rate constant 4, forget this one in the middle for the moment, and chromium 2 and chromium 3. So you see that. Now, can someone explain to me why is that? What's happening? What's the difference?
Where the new electron goes?
Mm-hmm.
Well, in the first one, the the new electron. Let's say we lose an electron from the bonding orbital,
Yes.
and then the other one from the anti-bonding orbital.
You're on the right track. You're on the right track. Yes.
Is there an electron that's big band as well?
Yeah.
And one that's alone.
These are all contributing factors, indeed.
But also antibonding has higher energy, so it's lower kinetic rate.
Well, antibonding, I mean, it's a bit misleading because one is tempted to think, well, you're taking an electron out of an antibonding orbital, it should be easier. But the reason is, look at where the action is. Here we basically, as you said, we're basically adding or taking an electron away from a bonding orbital, a T2G orbital. Here, what are we doing? In the one case on the right, we've got no electrons in the antibonding orbital. And on the left, we've got one electron in the antibonding orbital. Now that's a big difference, because here I'm not populating the antibonding orbitals, and here, in this redox state, it is populated. Here, actually all I'm doing is taking an electron in and out of an already populated orbital. You see that? Now, there are consequences for that, and the consequence is that there is a large amount of structural reorganization required energetically for this process to take place versus this process. Because think about it. Here I have no electrons in the antibonding orbital, right? Which means the bond lengths are going to be probably a certain, let's say a certain length. If I now put an electron in and I'm populating an antibonding orbital, what's the consequence going to be? The bond length is going to get probably longer. And because that bond length gets longer, remember this is all happening in solution. You've got water molecules surrounding the complex. Those water molecules are going to have to move away. It requires energy. So there's energy requirements here because of structural reorganization. And the symbol we use for that is called lambda. Lambda is the symbol for structural or for reorganization. We call it the reorganization energy, right? Okay, so that's why we have this discrimination. It's you've got to look at the redox, the electron configuration in the product and the reactant. In this case, the product and reactant happen to be the same thing. It's called a self-exchange rate. And based on the arguments I just presented, you can sort of rationalize your way through the through that. Here we have a slide which illustrates this, I think, very well. That's nice and clear. So here we've got, again, a slide showing a series of metals and looking at the self-exchange rate of the electron transfer process between two of these, right? So let's have a look at some trends here. Look at this. Cobalt, hexaamine, 10 to the minus 6, right? 10 to the minus 6. Right, and let's look at something that's got a much higher rate. Tungsten, hexacyanide, okay, yeah, well that's 8 coordinates, not so easy. Let's see.
Iron, hexa, water?
Yeah, let's take this ruthenium. Hexaamino ruthenium, 2,800, and yeah, that's a good one, and cobalt. Ruthenium, and yeah. So what do you guys think? How can we rationalize those big differences, orders of magnitude, in the rate constants associated with the electron transfer reaction? Let's take this one here, this ruthenium hexaamino, and let's take the cobalt. I mean, look at that. That's a dramatic difference. 7 orders of magnitude. 6, 7, 8 more. You know, these are big differences. Why? Well, let's think about it. Cobalt, ruthenium, hexa amino 2 plus. Let's draw that.
The same as the iron.
Ruthenium, NH3, 6, 2 plus, 3 plus, because that's not what we're doing. We're taking the ruthenium hexaaqua 2 plus and ruthenium, two of them, and they're exchanging an electron. That's why it's called a K11 value, a self-exchange rate constant. All right, so the value associated is 2,800. What's the electron configuration of ruthenium 2? It's octahedral. So what's the electron configuration? Ruthenium is in group 6, group 8.
So 60 electrons?
So is it going to be high or low spin? No. Low spin. We had this discussion yesterday. Remember, we're doing ruthenium chemistry in the lab. So it's low spin. Ruthenium, beautiful diamagnetic T2G6. Now, what is ruthenium? So that's ruthenium 2 plus. L6. What is ruthenium 3 plus?
That's electron in each of the C2 and E2.
No.
One unpaired electron in the T2G.
That's ruthenium 3. So what have I effectively done? I've taken an electron in and out of an already, of course it's going to require energy, but I've essentially just taken an electron out of an already existing and occupied orbital. Will that require a large amount of reorganization in terms of bonds changing, energy requirements of the solvent, cage around it, etc.? Yes or no? No, not considerably. Not considerably. So we have a rate constant of 2,800. There it is. Now let's look at, in dramatic contrast, cobalt, hexaamine 6, 3 plus 2 plus. So, cobalt. So cobalt, so we're looking at the self-exchange rate constants associated with this complex. It's also octahedral, so you can draw a crystal field splitting diagram for that. You see all the stuff from the course last fall is essential. Right, cobalt 2. Cobalt is group 9. How many electrons does cobalt 2 have?
7.
7. Does it have 7?
That's the
So cobalt 0 is D9. Okay. Cobalt 1, D8, D7. Cobalt 2 is D7, yes. Of course it has to be, that is the logical electron configuration. Now what is cobalt 3?
Without the
EG.
Exactly. So this is cobalt NH3 6 2 plus and cobalt 3 L. Well, let me just write it down. I'm being lazy. Cobalt NH3 6 2 3 plus has that electron configuration. Now, is there a big difference in the electron configurations? Yes. Here I'm populating an antibonding orbital, here I'm not. To go from this state to this state means a big difference, a big change, because if I go from here to here, I'm populating an antibonding orbital. That's going to change the cobalt water bond length, or the cobalt oxygen bond length, which is going to require energy. And it's going to move all the water molecules in the solvent cage around the molecule, which is also going to require energy. It's going to need more energy, structural reorganization. And that is why it has such a very low, comparatively low, several orders of magnitude bond rate constant. Okay, so I think you understand the notion of outer sphere electron transfer reactions. And I want us to have a look briefly at inner sphere reactions, which are very important. And like I said, in the case of an inner sphere process, we require a partner that is substitutionally labile, and we require a bridging ligand. So here we have the example of a cobalt complex and a chromium complex which are undergoing an electron transfer reaction. Now, the one reaction partner is inert, and it bears a ligand that's capable of forming a bridge, chloride. They're famous for doing so. They can form a bridge between two metal centers. Other suspects are, for example, SCN ligands, thiocyanates, and so on, can also form bridges. Point is, you need a bridge, or a ligand capable of bridge, and an inert and a labile reaction pair. These are the products that result. So notice what's happening. The chlorine is being transferred to the chromium, the and there's an electron transfer process going on there. Okay? And the water molecule that was displaced in the formation of the bridge formation, goes and then occupies that vacant coordination site that results from the chlorine transfer. You see that? So they swap. Everything swaps. What also swaps is the fact that you start off with the cobalt being an inert reaction pair. After the electron transfer has taken place, it becomes labile. And the labile chromium complex, after the electron transfer and picking up the chloride, becomes inert. This is incidentally what the intermediate would look like, right? This bridged intermediate, which we saw on the free energy surface a moment ago for this inner sphere reaction process. Here we have another example with iridium. So here we have an iridium complex reacting in an electron transfer mechanism with chromium. Same thing, right? Exactly the same thing. We end up, this over here is inert. Why is, labile. Why is this hexa-aquachromium 2+, why is that complex labile? Substitutionally labile, why? Why is that labile?
It's got an electron in the
Yes, yes. We're populating an antibonding orbital that makes that easier to do substitution chemistry there. This one is totally, this is dead as a doornail. Why? Because it's only got electrons in bonding orbitals, no antibonding. So chances are you can sort of, just by looking at those two, using a bit of hand-waving arguments, say, well, this is going to certainly be more labile. And that's exactly what happens. One of these chloride atoms forms a bridge with a chromium, the water is displaced, and you end up with this situation after the electron transfer has taken place. So, yeah, I think that's important. So those are the requirements for an electron transfer reaction to take place, bridging inert reaction partners. Now, a very interesting discovery was something that we will probably discuss a little bit later on in the tutorial. But sorry?
See the iridium, the last one. The products of this, which one is inert and labile?
Well, this one over here. I mean, although the EG orbital is not really populated, is a little bit more inert than this one, right? It's I mean, overall, it's a little bit different in this case because there's other rules for lability. It's not just labile if the EG orbital is populated, right? That's sort of a very oversimplified view. But if, for example, you have 3 unpaired electrons in the T2G orbital, it's also a little bit more substitutionally labile than if you, for example, have a closed shell electron configuration.
Why is there no ligand exchange?
But here there's no ligand exchange, exactly.
But why is that?
There should be, shouldn't there? That should go there, and the water should go here. So those should be iridium. Yeah, you're right. So that should be iridium Cl5, Cl5H2O, right? And chromium H2O5Cl. That's the products you would expect, yeah.
Where with the first one? Why did the NH3 get substituted for why? Yeah.
Well, no, it didn't. We started off with 5. Yeah, okay. No, that should be NH3. Yeah.
Because it does say the reaction that they is the plus 5.
No, this should be NH3. Oh, it does say that they were displaced. Yeah, it does. Well, I think what's basically happening there is two processes. The one is the electron transfer, and the other is a simultaneous substitution mechanism. But I would forget about that. Basically, the first step, the products resulting from the electron transfer are NH3, right? So that's NH3. And yeah, probably if you do this reaction then in an aqueous medium where there's lots of water floating around, there's going to be, by an Eigen-Wilkins mechanism, a subsequent substitution of all the ammonias with waters. That's what's happened there. It's basically an electron transfer process followed by an Eigen-Wilkins type substitution mechanism. Point is, I don't want to confuse the issue. Basically, this is what you form. It cleaves. The chlorine goes to the chromium, as you see there. You're left with a cobalt pentaamino thing here, and the free coordination site then gets taken by the water molecule that was displaced here. So those are the products, right? Maybe I should just write that down. So the products of that reaction at the top, immediately following the electron transfer, will be cobalt, NH3, 5, H2O. Okay, 2 plus. And chromium, H2O, 5Cl2 plus. Yeah. What will then happen subsequently, because it's done in an aqueous medium, as I said, is that this will probably react then in a subsequent step with water. Because it's labile, you see that's the point, because it's labile, and if you're doing the reaction in an aqueous medium, by Eigen-Wilkins type mechanism, we'll have the substitution. That's the point. That's why you end up with that. Those 2 steps. But I don't want to discuss the substitution, just the electron transfer. Okay. So that, guys, is essentially how electron transfer takes place. Now, what I wanted to mention is it's a beautiful work done by a guy named Tauber. And what he basically did is he discovered a way of proving the inner sphere mechanism. And what he basically did, I want you guys to sort of look into this, it's called the Tauber complex, is he synthesized and isolated a complex that actually has 2 ruthenium centers of different oxidation state with a bridging ligand. He could isolate it. So the purported intermediate, or the speculative intermediate we've been looking at, that bears this bridging ligand between the 2 metal centers, one labile, one labile, one substitutionally inert, with different oxidation states preceding the actual electron transfer. He actually did that. He isolated a model complex which shows that that's in fact the case. And I think that's a very important discovery, and there's a synthesis associated with that complex, which I think is something that I'd like you to look into as a homework exercise. Now, the last thing I want to discuss today, all right, is something called Marcus theory. Now, there was a scientist. Now, Marcus theory was originally designed for outer sphere reaction transfers, electron transfer reactions. And Marcus won a Nobel Prize for this work. And basically what Marcus theory really, I don't want us to go into too many details with us. I just want you to have sort of been exposed to this. Marcus theory is a way of explaining electron transfers, particularly for outer sphere reactions, because with inner sphere processes it becomes very complicated, remember, because you're forming a molecular orbital between the two metal centers. That complicates things considerably. But for an outer sphere electron transfer, what Marcus said is, well, let's just imagine that the reactants and the products, in other words, if we imagine a self-exchange between ion 2 and ion 3, so two ion centers, one ion 2 plus, one ion 3 plus, like we've just been looking at, you can actually imagine that you can represent the potential energy of the reactants by these Morse potentials, right? So this is energy and this is reaction coordinates, if you like, or actually vibrational coordinates. You can represent it by these free energy wells. Okay, now you're all doing, at least some of you are doing quantum chemistry. I don't want to get into too many details because this is very complicated. Don't worry too much about this. But what this curve over here represents is essentially the potential energy, if you will, of the reactant, and this is the potential energy of the product. In other words, this is the, let's say, oxidized form, this is the reduced form, if you're considering a self-exchange. Now, basically, where these two curves intersect, right, that over there, from the bottom of the reactant curve to the point where they intersect is the free energy of activation of the electron transfer process, right? And the difference in energy between here and here is the free energy change of the electron transfer reaction. That's Marcus theory. Now, what is lambda? We encountered this term lambda earlier. What is lambda? Reorganization energy, yes. And lambda actually is, and you can see from, that's the beauty of Marcus theory, you can immediately infer the reorganization energy, which essentially runs from the bottom of this free energy well here, of this Morse curve here, to where it intersects with the reactance curve there. That is reflective of the so-called reorganization. And the reorganization energy is split into two subterms: structural reorganization and vibrational reorganization. So there you see it. It sort of turns up. And the beauty of Marcus theory, in fact, is, I'm not going to go into too many detail. I mean, I did this really in detail in Bonn with the students. We really looked at Marcus theory in detail. We even derived the relationship between free energy and lambda. So there's a relationship between the free energy change of the reaction and also the energy of activation and the structural reorganization and stuff like that. I don't want to go into too many details. I just want you to sort of appreciate that Marcus theory is a theory that one commonly employs for outer sphere electron transfer reactions. And as a matter of fact, there exists something called the Marcus equation, which you see at the bottom there, which enables one to establish the rate constant for an electron transfer between two species, or two complexes, if you know the self-exchange rate constant for those two complexes. You know the the rate constant, the equilibrium constant for that reaction, and F, which is sort of a fudge factor, which we generally set equal to 1, this equation enables one to actually calculate the rate constant from Marcus theory for an electron transfer reaction. Okay. Now, as a matter of fact, I have an example of that, which I want us to have a look at, using the Marcus, this Marcus equation, also sometimes called the Marcus-Hush equation, to calculate the rate constant. I just need to find it. Here we go. Right. That's an important relation. Right? And this F over here, as I said, is sort of a fudge factor, F for fudge factor. Okay. Actually, it's not that simple. It's a factor that takes collision cross-section into account and all sorts of other terms. As a matter of fact, I'll write down what F is in a minute, but it turns out that you can approximate it as 1. All right, so now let us employ the Marcus equation to estimate the electron transfer rate constant of the following reaction. So this comes from Marcus theory. Let's just turn on the light again. Okay, this comes from Marcus theory directly. This is a beautiful result. Beautiful in its simplicity. So let's suppose the question is to calculate the rate constant. The rate constant for the reduction of cobalt BP, which is bipyridine, 3 plus by cobalt terpene. These are just ligands, polydentate ligands. Right. So these are two different complexes. I'm basically doing an electron transfer of a cobalt terpene, which is a tridentate ligand, to BP, which is a bipyridine. Right. These are basically arene, nitrogen-containing arenes. I guess you've seen them in organic chemistry. All right. So basically, we know that the K value, the equilibrium constant for this reaction, is 3.57. This is something that can be experimentally determined. The K11 value is 18 mole per mole seconds, and the K22 value is 48.
What is the equilibrium constant referring to? Back to what equilibrium?
The equilibrium constant is what do you mean? What is it defined as?
No, it's the equilibrium in between the two complexes and between self-exchange for one complex. I don't get it.
The equilibrium constant, sorry, the equilibrium constant is the equilibrium constant of this reaction.
Okay.
Right? In other words, let's write it down. Cobalt BP 3 plus cobalt terpene 2 plus. Product will be cobalt BP for bipyridine 2 plus cobalt terpene 3 plus. So the K, we can call it K12 because the 1 refers to a self-exchange and the 2 to the self-exchange for the cobalt terpene. It's going to simply be the concentration of that times that over the concentration of that times. And that can be experimentally determined. You end up with a value in this case. Of course, you have to specify the temperature, so this is done at 0 Celsius, incidentally, of 3.57. You can determine the self-exchange rate constant of cobalt BP 3 plus 2 plus, and you can determine the self-exchange rate constant of cobalt terpene 2 plus 3 plus, and you get values of 18 and 48. The units are liters mole seconds. Because it's kinetics, don't forget liters per mole seconds. And if you basically plug those values into the this beautiful equation, where K12 is let's call this K12, is the rate or the equilibrium constant of the overall reaction, and you solve, you get a value of 56 moles liter seconds, the rate constant. Point is, you can estimate the rate constant of an electron transfer reaction between two species if you know the equilibrium constant and if you know the self-exchange rate constants of the two species participating in that electron transfer reaction. So this K11 value is for the self-exchange, just to really pin this down so you guys understand this, for that process, 2 plus 3 plus, that's a self-exchange rate constant. And this is the self-exchange rate constant for the terpene, which is a tridentate arene ligand, 3 plus 2 plus. Now finally, coming back to this notion of F, which I said is a fudge factor. It is a fudge factor. It generally equals 1, but it's defined, just for those of you that are interested, as the logarithm that's what it's defined as. That's the definition. So it is a term that takes essentially, really Z here is the collision cross-section. If you calculate this for most reactions and solve for F, the value approximates 1, believe it or not. But that's the case. So we don't have to worry too much about that. We can always assume F is 1 and plug it into the Marcus equation. The Marcus equation is very simple. I mean, it's just the square root of, to get the K, so we're trying to get K12, right? The K is the rate constant. So K12 is the square root of F, K11, K22, K, big K12, which is the equilibrium constant. And so that's Marcus theory. So whatever let's summarize everything that we've looked at in this part. Innosphere and outosphere electron transfer reactions, the differences, the characteristics, formation of the mechanism, free energy surface, very important, precursor and successor complexes and all that. And then we moved on to look at Marcus theory and the Marcus equation, which rationalizes particularly outosphere electron transfer reaction processes, but you can do it. In fact, Marcus theory can be extended to any reaction at all. It's a beautiful theory. He won a Nobel Prize for it, I think in 1986, I think, for this work on electron transfer. And this Marcus theory that he developed has been widely used, particularly in biochemical systems, to explain certain mechanisms. For example, photosynthesis, right? Which involves a lot of electrochemistry, bioelectrochemistry. Marcus theory, it turns out, explains that very well. In fact, that's one of the reasons why he developed this theory. I think he was a biophysicist. And he wanted to understand photosynthesis from an electrochemical perspective better. And this theory does a very good job of explaining electrochemical processes in biosystems.